Okay. So welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce you to tonight's speaker, Kasia Rejzner. Kasia is a reader in mathematics at the University of York. She received her PhD in 2011 with distinction at the University of Hamburg, notably accomplishing this in less than 2 years. I don't know if I've heard of anybody doing this before. After this, Kasia went on to postdocs in Hamburg and Rome before finally taking a permanent position at the University of York. Dr. Rejzner was awarded an Emmy Noether Fellowship at Perimeter Institute in 2015 to 16 and has been a visiting fellow there since 2018. Kasia is aimed for arguably the most challenging topics there are in mathematical physics, namely algebraic quantum field theory with a special focus on understanding interactions between quantum theory and gravitation. In 2016, Dr. Rejzner published a book entitled Perturbative Algebraic Quantum Field Theory, an Introduction for Mathematicians. And tonight we are lucky enough to have that Kasia will be telling us about a project she worked on together with collaborators that stretches across several areas of interest in foundations of physics. Her talk is entitled Quantization, Dequantization, and Distinguished States on Causal Sets and Beyond. Now, before we begin, I would like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it is not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Kasia, anytime you're ready.
All right, thank you so much. Thank you for this very nice introduction. And it's a pleasure to be here, sort of virtually. Yes, so I want to tell you something about my joint work with Eli Hawkins and Christoph Minz. And I've seen at least Eli here. I hope that Christoph is also joining us. I have to say that, well, there was, it's a topic at the intersection of several fields and several sort of mathematical worlds. So I'm not going to be disappointed if I don't say everything I want and instead just try to answer your questions. And well, since my collaborators are here, they can also probably throw in a few comments. So please, if you don't know something, just ask. Okay, so let's get going. So let's start a bit with quantization. And well, it was already mentioned that I work in algebraic quantum field theory. This is indeed the case. So this is a framework for understanding conceptual foundations of quantum field theory, which in its own right is a difficult problem. So the basic idea goes back to Haag and Kastler. So this was proposed in the 60s, which kind of postulates to define a model of quantum field theory by associating to each region of Minkowski spacetime an algebra of observables that can be measured there. So here is a schematic picture representing that. And then one of the sort of basic axioms there is that if we have larger regions, then we have more observables. So this is the one here. And okay, can I annotate the PDF? Is that something I can do? I hope so. Let me try. Do you see what I write?
Yes.
Okay, so another important axiom is causality. So if we have two subsets here like that, which are space-like separated, so you know I can put the light cone in here, then I expect that the observables associated to these regions are kind of independent. So this is described by Einstein causality, namely that the two algebras commute. Okay, so causality is one of the sort of foundational features in this framework. Okay, so now how can we generalize it? Well, first thing, this can be generalized also to curved spacetime, so to manifolds. But what I want to focus on today is a slightly different generalization, namely generalizing this to discrete structures. So building quantum fields, quantum field theories on manifolds in what one could call continuum is notoriously hard because of UV divergences, things that happen at, when we have 2 points close together and fields localized at the same point, so to say. Now, this can be avoided if we work on a discrete set. So here is the proposal. So replace the smooth manifold with a discrete set of points equipped with the causal order relation. So this causal order relation is actually crucial to make this thing workable. Sorry, I'm just trying to figure out how this whole thing works. Okay, now I think I understand. All right. So this was worked out in a paper by Edmund W. Heath, Christopher Fuster, myself, and Nick Woods. Was a while ago. So that was like the first take on, all right, so can we construct something like algebraic quantum field theory on these discrete structures? I owe you a definition, so let's be a bit more precise what I mean by a discrete set of points together with a causality relation. So C is the set of points. We think of them as events, and the relation is a partial order, so it satisfies these properties. Here it has to be locally finite, and that's essentially it. That's the only thing that sort of survives from the concept of manifold. Okay, so this is the sort of playground I want to focus on.
Yeah, can I ask
yes.
a quick
Yes.
question? So
sure.
in Sorkin's causal set work, they've got this process where they do a sprinkling into encapsulated space. Is that something that is required in what you're doing, or can you kind of is it more general what you're doing?
This is more general. So you can construct quantum fields. I mean, in this sense, so algebraic quantum field theory on like a fixed causal set. So let's say a regular lattice, regular diamond lattice. This is perfectly fine. Now, we have done actually a lot with sprinklings. So there's another paper by Chris, Eli Hawkins, and Christoph Minz and myself, where we actually looked at the structure of those sprinkled sets and analyzed, how this affects the quantum dynamics that we proposed. So yeah, I mean, sprinklings are a pretty good sort of playground, but it's not necessary. I mean, like here, this is maybe, the difference between considering sort of quantum field theory as a covariant thing that works on all manifolds of a certain type versus quantum field theory on a fixed manifold, right? So you can have quantum field theory on a fixed sprinkling, or a fixed causal set, which is a diamond lattice, but then you also want to really study properties of that whole thing on that whole ensemble of sprinklings, right? To take expectation values and such. Does it make sense?
It does, yeah. Thank you.
All right. Yeah. So that's the setup. And now, so for me, kind of the good motivation to look at it was well, apart from having a new way to construct quantum fields on sprinklings or causal sets more generally, I wanted to understand a bit better quantization that could potentially be applied in quantum field theory, but in context where everything is nice, finite, and no UV divergences are present. So in particular, because of Eli Hawkins and his interest and expertise in geometric quantization. Hi, Eli. I thought, well, maybe that's something one should try out on these discrete structures, see how it works, and maybe we learn something about what to expect for quantum field theory. So yeah, there is a sort of long-term goal. And geometric quantization is nice because well, it's a natural way to construct quantum models from classical data. So as quantizations go, this is particularly pleasant. So the paper I want to focus on is called Quantization, Dequantization, and Distinguished States by Eli, Hawkins, Christoph, Minz, and myself. So here is the archive reference, where we start from a symplectic vector space with an inner product, and then construct the quantum algebra equipped with a distinguished state. And I want to compare this construction. So there will be a lot of technical stuff, I'm afraid, but in the end, I want to compare that with another completely different approach by Raphael Sorkin of how to construct distinguished states on causal sets. So this is the end goal if we get there. So compare the results with something known as the Sorkin-Johnson states. And we have indeed shown that with the same input and a different condition for what does it mean to be distinguished, we indeed reconstruct the same state. Okay, so let's get started. There's going to be something about quantization, dequantization, and all that jazz. So let's start with the sort of the simplest, the cheapest one to obtain, which is formal deformation quantization. So and it's still very difficult. So formal deformation quantization is the idea that, well, you start with a Poisson algebra, and this is equipped with a pointwise product. So this is sort of your classical theory, and you deform this to a star product that represents the operator product of your quantum theory. The formal bit is that everything is a formal power series in H bar. Okay, so here is a bit more detail. So starting with a symplectic manifold, which is going to be the context we are going to work with later on. Oh, sorry, there's some background noise. So we start with a symplectic manifold, and the star product is defined on the space of formal power series in smooth functions there. And well, it takes this form. So it's power series in H bar, right? So we can expand it in H bar, and we have those maps B, K. And now these are bilinear maps, which in addition fulfill certain conditions. So one of them is associativity. This is an important bit. And another one is the fact that, well, in the lowest order, zero order in H bar, this is just a pointwise product of functions. So that's classical theory. Okay.
Can I ask, would it be really problematic if B wasn't linear?
Oh, well, so here it's a bit of, yeah, I mean, in the end, we want this to be differential operators. So these things tend to be linear. Let's see. Well, I guess the problem might be associativity. And also, like, okay, I mean, you want this thing to be yeah, I mean, typically you expect the operator product to be a bilinear product, right? So in the context of quantum mechanics and quantum field theory, I don't know what this nonlinearity would represent. So yeah, do you have some particular
No, I'm just curious. I'm just curious
yeah.
about the generalizations.
I don't know generalization in that direction. Maybe Eli knows. If Eli knows, then Eli can speak up. I assume Eli doesn't know. But thanks for the question. All right, so we have that, and then this product. Well, other things that we want from this. We want this to be compatible with the Poisson structure, which defines your classical theory. So classical theory, like classical mechanics, right? We have the canonical bracket. This is the Poisson structure. It's the Poisson bracket. So the commutator, right, should be in the first order in H bar. The commutator should be I times the Poisson bracket. So that's this condition. Okay, we also typically want it to be unital, self-adjoint, right? These are obvious things you want to ask for. And differential, that's what I mentioned before. So all these BKs are by differential maps. They are differential operators, which is also kind of useful. Okay, I will show the example of that in the context of causal sets a bit later. But first, I have to power through some more definitions. Any questions at this point? Okay, so let me move on to the strict deformation quantization. So here we have a bit of change of pace. So maybe I should have mentioned this before in the context of algebraic quantum field theory. Those algebras we associate to regions are typically, and in the best case scenario, C-star algebras. Now it occurred to me, should I explain C-star algebras?
Sure.
Okay, I mean, probably everybody knows, but if not everybody knows, then, well, I mean, these are topological algebras. These are Banach algebras with involution and the C-star property, meaning that I'm always doing these things wrong. I wish I had a board. That would make me happy. Let's see. Come on. Come on. Okay. All right. So the norm has to be continuous. That's being Banach algebra, and the thing is complete with respect to the topology induced by that norm, and this is the C-star property. So it's a sort of nice behavior with respect to the involution. Now, typical example of a C-star algebra is the algebra of all bounded operators on a Hilbert space. So this is the prototypical example, which is kind of defining. You might then ask, why bounded? I mean, what about unbounded operators? Well, I guess the postulate in algebraic quantum field theory is that, everything can be sort of reconstructed from bounded operators. So, for example, if you have just a free field, free scalar field, then you want to be able to, well, I mean, you can talk about field operators, which would be unbounded, but instead you can construct Weyl operators, which are bounded. So, and then fields are just obtained by taking a derivative. So in a sense, the idea is not that, everything is bounded, but more or less that all the information can be reconstructed from bounded. Okay, that was a little digression because I thought, well, C-star algebras is maybe something worth elaborating on. And this is also a key sort of ingredient in, well, strict deformation quantization. So this kind of, yeah, makes, well, I mean, there are definitely some connections and some ideas which say these approaches have in common. Okay, so yeah, so to define strict deformation quantization, then H bar is still present, but now it's not a formal parameter. It's actually a number belonging to some interval in R. This interval including 0 because we want the classical limit. And here the strict deformation quantization is given in terms of a family of C-star algebras, A, H, labeled by this parameter. So, and this is now a number. So you have these various C-star algebras associated to H. Now, okay, so quantization. Okay, so what is a quantization? In this setting, well, in short, it's a way to obtain quantum observables from classical observables. So it can be described in terms of a map Q, or rather a family of linear maps from A0, which is a classical algebra sitting in A0. So this is where the H bar is equal 0 situation, to this sister algebra of quantum observables AH, parameterized by H bar. So for each H bar, we have a map. And this has to be compatible with involution and also the unit if the unit is around. Okay, so that's the idea of quantization in the more sort of precise terms. Now, dequantization, that's a funny animal. So that's going the other way around. And again, this is a family of linear maps from AH to A0, respects involution and respects unit. So both of these guys are going to feature. Okay, maybe let me pause for a second. Any questions?
I think Francis has a question. Just one sec here.
Oh yeah, I don't see.
Yes.
Yeah. So if you
I'll handle the question.
Oh yeah, no, I see.
Please, I wanted to understand very well your interval, your I, what the definition for your interval I, because it's I can see you are saying that the Planck's constant, that's the H bar, is a member of the I, and you gave that the I is a subset of the real variables or real numbers. So what is the definition of your I, since you are also putting the Planck's constant to be 0? What is your definition of the I?
I is just okay, so this enters the particular example, the particular model you're trying to quantize. So it might happen that, given a classical theory, right, it can be quantized only for certain values of H bar. Okay, so the I is those values of H bar for which this can be quantized.
Okay.
So this is not arbitrarily fixed. This is somehow fixed in the particular theory.
Okay.
Mm-hmm.
So Rob Mann has a question. I'm just going to unmute here 1 second. Here.
Hi.
Yeah, hi, thanks.
Hi, Rob.
Kasia, I'm just wondering, is the, I mean, this thing looks like it's perturbative in H bar. Is that right? Or is this in general non-perturbative?
This is non-perturbative. This bit is non-perturbative because here H bar is really a number, right? So each of these, so these algebras AH are not a formal power series in H bar. H bar is really a number. So you can.
It's just that the star algebra appears to be perturbative in H bar, or a power series, right?
Yeah. So what you're thinking about, I think, is more about the formal deformation quantization, right? So formal deformation quantization, H bar is a formal parameter, but here H bar is really a number. I mean,
okay.
Sometimes,
all right.
So actually, maybe the next point will clarify it somewhat. So here is the definition of the star product related to a given quantization, and so here, well, this is corresponding to the quantization Q. So star Q. If it exists, right, then this is a star product with the operators BQ at each level, such that, and here is, well, okay, so here is a definition of what happens at kth order. So in the sense, you want this star product to converge to this God-given product that lives in your sister algebra, and this is expressed in this condition here. So the quantization map Q takes you a function to an element of your algebra. Okay, if I get the annotating tool right. Okay. So this now lives in the algebra, so it's an operator. Here I multiply it with another operator, right? And then this term, I take two functions. These are functions. I apply to them this BQJ, so a corresponding order in the definition of the star product. So this is again a function. Everything is, you know, non-perturbative at this stage. Nothing is in terms of formal power series. And then I go to the quantum algebra with QH. And then I compare these two things. So star product star Q is something I use to multiply functions. And that should emulate what happens if I multiply the corresponding operators living in AH. And here, like all these maps, all these terms are actually make sense for each finite value of H bar, which, well, I mean, as long as it belongs to that interval where things are well defined. Does it make sense? No objections? So I think that in the sense that maybe kind of makes a connection between this sort of more abstract C-star algebraic idea and well, the actual star product of functions.
I think we've got a couple
yeah.
more questions, actually, if you don't mind.
Yeah, sure. Yeah, absolutely. No, that's good.
Okay.
That's what we're after.
Very good. Okay, so Francis Howard, go ahead.
Okay, Doc. Please, with the dequantization family of linear maps that you have a family of linear maps that's from the U of H into the U of 0.
Yes.
Is it where you are putting your H to approach a limit of 0, as in the range you gave for the I, where H can also be 0?
Yes.
Okay, so in that case, I've seen that you ended it that the order remainder vanishes in the classical limits. Are you saying that when H approaches 0, all the R Q of K goes to 0?
Right. So yes, that's correct. Because I mean, or so if I go back a bit, maybe that becomes more clear. So this was the perturbative story, but I think it's sort of yeah, good way to see it. So these are these BK coefficients, right?
Yes.
And so if we go with H bar, well, okay, if that was non-perturbative, right, and we went with H bar to 0, then yeah, all these like higher order terms would vanish, so we would be left only with B0, which is the pointwise product, which is the classical product.
Okay.
If that makes sense.
Yes, right.
So there's the same kind of thing you want, of course, in also non-perturbative situation.
Okay.
Okay, so Causal has a question. I'm going to unmute you. Go ahead.
Yeah. I was wondering about the non-commutativity of the operators in this big norm that you have defined. So will it play any role here, or is it
so both you can notice that both are in the same order, so to say.
Right.
So yeah, it does. I mean, like, okay, I mean, if it converges one way, it should converge the other way as well. But yeah, I mean, here the order matters, because you have these are operators, so the product is indeed non-commutative, so the order matters.
Okay, so F1, F2, I mean, when we apply the map B, we are considering the star product, which I assume is non-commutative, I guess.
Right.
That's what,
Yeah.
Okay.
Yeah.
Yeah. Thanks.
Thank you. Any more questions?
I think Francis Howard, one more. Okay. Wait, one quick one. Go ahead. Francis Howard? No, I think.
Or is it the same question?
I think, yeah, maybe he just has his hand up from before. Okay, but go ahead.
I'm not sure I've raised up my hands. I'm okay though.
Okay.
Okay.
Cool. Good, very good. All right. Okay, there's always a bit of definitions, so it's good to have this sort of settled. So yeah, so the final bit is the definition of what it means to be infinite order strict deformation quantization. So a quantization Q, so this family of maps from classical to quantum, so to say, is this infinite order strict deformation quantization if, well, there exists something called a continuous field of sister algebras. I decided maybe not to elaborate on it too much because it's kind of technical, but it's essentially, well, I mean, it's similar to having like a bundle of sister algebras, actually. And there is a notion of being a section in that continuous field of sister algebras. So again, we want, well, I guess sections are things that behave relatively nicely. They can be added, multiplied, and yeah. So I guess this is a kind of niceness condition. The quantization star product has to exist. So this, well, I mean, what I showed on the last slide with this convergence of these coefficients, the star product should be Poisson compatible. So it really should be a deformation of, you know, your classical theory with the Poisson structure. And okay, I mean, there's much more to that, I'm afraid, but I feel like maybe this is enough of this sort of very, very technical stuff for the time being. But yeah, so what we're aiming at, just to maybe summarize what we want to be able to construct this infinite order strict deformation quantization. And then now I want to kind of pass to the concrete example we looked at and maybe try to explain how these structures arise and how to connect it with other things. So yeah, so that would be the next section, unless there are still questions to the previous section. Okay, but thank you very much for the questions. This is always very useful.
Actually,
all right. So,
you do have a question. So Hashams, I'm going to unmute you. Go ahead.
Yeah, I have a question about quantization and deformation. Is there any condition like continuity or a smoothness on that part? I mean,
yeah. There is. I'm just not maybe giving all the details there. So for the precise statement, I would send you to our paper where we spell it out in all detail. Oh, Eli wants to comment on it. Yeah.
Go ahead.
Am I unmuted?
Yes.
Yes.
Okay. The condition of having a continuous field of C-star algebras is the continuity condition.
Yeah.
And the condition that the star product exists is a smoothness condition, at least smoothness at h bar equals 0. So in a sense, yes.
Yes. Thank you, Eli. Does it answer the question? Yes, no, maybe.
No complaints. So I think that's
I think he's muted.
No complaints. No complaints. If no complaints, then let me just go ahead. Yeah, oh, just to get some idea of timing, how much time do I have?
It's pretty flexible. So if you run over a little bit, it's not a big deal.
But the default is 1 hour without questions or with questions?
So the default is say 1 hour without questions, and then usually the questions kind of run us over the hour after that.
Okay. Yeah, no, that seems reasonable.
Okay.
Looking at how things are going. Oh, now something happened. Sorry. My computer is very low on battery, so I think I should try to keep in time. because I really don't have anywhere to charge it nearby. But let's not panic. It's going to be fine. Okay. Come on. All right. So here is the story. So yeah, scalar fields on causal sets. So we start with a fixed causal set. Then scalar fields, as one would guess, they're maps from this causal set to real numbers. And we call this space of such maps the configuration space of the theory. And if we have a causal set of finite cardinality, which is typically the case, and definitely it's, you know, what we can put on a computer, this configuration space is just Rn. So here observables are functionals on this configuration space. And well, I guess somewhere, you know, I have to mention this Poisson structure or symplectic structure that we will do later on. So this is coming from the dynamics, and we're talking free scalar fields. So there is going to be some green function, which is coming from a discretization of some normally hyperbolic operator. That's the whole story, how to get these things. But let's say that here, this is an input that we have. And they have certain properties. So there's a reason I name it E plus E minus. So E plus means that if I apply this green function to well, an observable which is localized in some region. Again, let me try to use oh, maybe not. It's moving. Okay. In some region, either causal set or actually the same goes with spacetime. Then if I apply to it E plus, and then I get something which is localized in that region together with its future. And E minus goes the opposite way. So that would be E minus. All right. And then their difference is something called Pauli-Jordan operator. Again, these concepts work both for manifolds and for causal sets. And here is the Poisson bracket. So we take derivatives of observables with respect to fields on causal sets of finite order. This is all like just finite dimensional ordinary honest to goodness derivatives. And E actually is a matrix, n by n matrix. So yeah, this makes sense, of course. And this is the Poisson structure we're going to deform later. So it's nicely coming from the dynamics of the problem. And well, this whole idea goes back to the idea of pairs, to define the canonical bracket as the difference between retarded and advanced response of the system. So this is maybe if you haven't heard about it before, this is something interesting in its own right, that it's a covariant bracket that can replace it's equivalent to the canonical bracket in classical theory. The fact it's covariant is very useful if you want to do it, say, on a causal set where you don't have splitting into space and time in any sort of reasonable canonical way. So it's a good way to define the Poisson structure for your classical theory. Okay, and then the star product, and here are the questions? No, okay. So here is the star product. Now, in the first instance, what was done was to construct the formal deformation quantization of that story. Or, well, if you don't want to be bothered with formal, let's just talk about observables which are polynomials. So this is not particularly great for sister algebras, but it's actually good if you want to just get an idea of what's going on with these structures. So one can define a star product, which well, I mean, either we restrict it to polynomials or has to be seen as a formal power series in H bar, which is given in terms of an integral kernel, and it's essentially an exponential of a bidifferential operator. Okay, so there is this operator of differentiating one argument, differentiating the other, and contracting with that kernel. So in a sense, well, you can now see an example of how these differential operators in the star product can look like. This is the simplest example where these come from an exponential of a single bidifferential operator with constant coefficients. Now, how do we get K? Well, that is going to be explained in the next slide. So yeah, so given K, we get the star product. Now, what is K? So here, this is given in terms of a matrix W, which is complex Hermitian, interpreted as the two-point function of a quasi-free state on the quantum algebra. So this is somehow connecting to states. The sort of imaginary part is given by the Pauli-Jordan function. So it's given by essentially the Poisson bivector, E, and H is some symmetric part, okay? So that antisymmetric piece takes care of the fact that the commutator with respect to this star product in the first order corresponds to the Poisson structure. And well, the way it's set up, the zeroth order here is just a pointwise product of two functions. Okay, so now there is a funny thing, of course, about the choice of this H. I haven't told you anything about how we choose this H. So there will be different products when you choose different H in that formula. So how can we restrict, the choice? Maybe there is some unique choice which is particularly nice. So let's see. Well, here is some sort of input from physics about what W could be. So yeah, so this I already said, that E is the imaginary and H is the real part. We want some positivity. So if we see W as a two-point function of a state, then it has to be positive. So that's one restriction. Then there is some notion of it being kind of like, oops, sorry, something fell on my screen. Something like solution to equations of motion. So this is this one. Well, another way of thinking about the choice of H, physically, this corresponds to the choice of normal ordering. If you have some experience with QFT on curved spacetimes, then you know this kind of a problem that, there are many states you could choose from. There is no like distinguished vacuum states. So you have to deal with something like that as well. Okay, so, and here is, at least in this situation of a causal set, Sorkin-Johnson idea comes to the rescue. So there is actually a unique, there is a distinguished way of specifying this W, which corresponds to having a distinguished state. This is what we want to talk about. So in this causal set example, W is the unique matrix satisfying the following. So this is this condition that the antisymmetric part gives you the Pauli-Jordan function. So the Poisson bivector. here's the positivity, but here is another one, okay, which corresponds to the kind of proxy for being a ground state. So this is like a ground state condition, and it's sort of well, emulated on the property that the vacuum state fulfills in quantum field theory on Minkowski spacetime. These are all matrices, and these conditions can actually be solved. So you can find, you know, I mean, this is very simple algebra actually, that you can find the W, you know, essentially given by these conditions. And that's what it is, right? So you have to, well, take some square roots here, but there is a formula. So this is the W, which corresponds to the Sorkin-Johnson state. All right, I think, okay, so that's it on the Sorkin-Johnson side. So that's another good moment to take a break. Any questions?
Okay, Hasham's, go ahead.
Yeah, so I have what the definition of observable. It seems that if I'm not wrong, you define observable as measures on configuration space. Is that correct?
No, that's not the configuration space you're thinking about. So here, literally, what I mean by configuration space is the space of maps. Well, here it's just Rn. The configuration space is Rn. And the observables are just smooth functionals on Rn.
Ah, I see.
So they don't have to be measures in any way.
Okay.
But yeah, I mean, I see where confusion is possible, because configuration space is also something different in mathematics.
Right.
Thank you. Any more questions? Okay, so let's pick up where we finished. So now, after this excursion into the Sorkin-Johnson world, let's say a few words about geometric quantization. And here, because you know, the time's precious, I will be a bit more sketchy. Okay, so with the structures I presented, you can actually get, well, I mean, a kind of object you obtain in the classical theory on a causal set would in particular give you a real symplectic space. More generally, a sort of input to geometric quantization would be any real symplectic manifold like that. Now, one defines something called the quantization bundle, which is a Hermitian line bundle over M. Oh dear. I'm going, okay, sorry. Would you mind, I will have to switch to my phone because I'm running out of battery on my computer. Is that all right? Sorry about that. That's gonna take a minute.
No worries.
But we are changing topics, so that's okay. Okay, I'm switching. Yeah, so I'm going to speed up a bit then. Okay, so right, so what's the structure? In principle, here in geometric quantization, we have this Hermitian line bundle. We have a connection, so that's going to be an important piece. And we have something called the polarization, which corresponds to taking certain subbundle of the tangent bundle of M. And there are some sort of prescriptions for constructing quantization and dequantization in that context. So there is something called Berezin-Teplitz quantization. So if you can, okay, maybe I didn't say that. Okay, so, okay. Yeah, so there's something called a physical Hilbert space, which is constructed from this space of polarized sections. So you have this line bundle, you have the choice of polarization, and then you have a space of sections that are sort of compatible with that polarization, which then you call H the physical Hilbert space. So given that structure, you can consider a projector from the space of L2 functions on M, or L2 sections of this, of LH. And then there is something called Berezin-Toeplitz quantization that is a way to, okay, so I wanted to just say a few words about this Berezin-Toeplitz quantization. So it's a way to assign bounded operators on this physical Hilbert space to classical observables using this projector from the space of square integrable sections. And this is a sort of compatibility condition here. You can see that if I have F, then applied to this Berezin, so F is a classical observable. If I apply to this Berezin-Toeplitz map, this should be the same as, and then act on some psi in the Hilbert space. This should be the same as acting with F on psi and then taking the projection. So this is sort of compatibility condition. And there is also, okay, so then, yeah, we can also define a measure so that tracing is the same as integrating with that measure. And we also have, well, sometimes we can also have the Berezin-Toeplitz dequantization. So if the measure defined, oops, sort of escaping me, okay. If the measure defined here exists, we can kind of reverse this process and we can define the Berezin-Toeplitz dequantization map. So this is it. So it's a map from, as it's supposed to be, so from AH to A0. And here, well, is the condition that it has to fulfill. Okay, so, you know, again, I don't really have time to go into these details anyway, but just the sort of crucial element here is that, well, there is this sort of canonical construction of these Berezin-Toeplitz maps. And actually the one we are going to focus on is the dequantization rather than quantization map. Okay, final ingredient. So if we have a symplectic manifold with an extra structure, which is a Riemannian metric G, then there is another geometrical object that we can use called the Bochner-Laplacian, defined in terms of the connection and the metric. And this actually has, well, this contains information about, well, this Riemannian metric and the symplectic structure. And there is a way to use it to get some distinguished states that I want to briefly describe. So, okay. Now, just to remind you that in this causal set example, there is actually a very obvious Riemannian metric that, well, you all know about. You might not realize that this is there. There is, of course, the inner product on Cn, right? So one actually uses this inner product to define what I wrote before as the ground state condition. So there was this condition W times W bar equals 0. Obviously that times is the matrix product, right? But implicitly we are here using the fact that we can multiply vectors and matrices. So there is an inner product structure on the space of, on the configuration space, right? On the space of functions on the causal set. So this is maybe slightly hidden, but it's there. And of course, therefore, we are in the situation described above, so we can define this Bochner Laplacian, and that's essentially what we used. So what we have done in our paper was to, find the spectrum of this Laplacian and use the lowest part of the spectrum corresponding to, well, in this case, a single eigenvalue to define this Hilbert space, physical Hilbert space H. So this Laplacian, sort of the lowest part of the spectrum of the Laplacian, distinguishes a state. Okay. And then in particular, what is this state? Well, explicitly it's given in terms of a linear map from your, well, as a state is, right, from the algebra, quantum algebra to complex numbers. And it's actually given in terms of this Berezin-Topliss dequantization. So you take A, which is in the algebra, dequantize, so go to the space of functions, evaluate at 0, you get a number, okay? And surprise, surprise, I mean, it was actually pretty neat that in the end, this number, this state is the same as the Sorkin-Johnson state that described before. So it's a completely different angle, it's a completely different argument at coming at this result. Okay, that's all I wanted to say. Thank you very much for your attention, and sorry for that last bit to be a bit sketchy. Thank you.
Thank you so much for a wonderful talk, Kasia. And I think you handled this very gracefully, considering there was surprisingly minimal delays given that your battery cut out on you. So does anybody have any questions? I have a quick one. So in your paper, you mentioned something about quantization, dequantization not being inverted with each other. And so I can see like you would have an operator ordering that could be one way that can you expand a little bit on kind of what kinds of scenarios can prevent it from being not invertible?
Yeah, so maybe actually, again, I will ask Eli to comment on it because he has much more experience in that, and I think he might have some examples in mind, or maybe Christoph.
So an example of non-invertible would be if you have, instead of a vector space as your classical phase space, you have, say, a sphere. And you can do geometric quantization on that. And the Hilbert space that you get is finite dimensional. So the quantum algebra is actually a finite dimensional matrix algebra, whereas the classical algebra of observables is infinite dimensional. So clearly the linear map from the infinite dimensional vector space to the finite dimensional vector space can't be invertible.
Sure, okay.
So that's an example of how it could happen.
Great, thanks.
Thank you.
Yes, but I think for the particular examples of causal sets, I think it is always invertible, I guess, for most of the settings that come to mind there. Yeah,
it's probably invertible, although the inverse isn't necessarily very nice.
Yes,
right.
Yes.
Maybe really its spectrum is kind of converging to 0. So when you invert it, you're making little things very big.
Yeah.
Does anybody else have any?
Thank you, guys.
Thank you. Teamwork.
Always good to bring collaborators.
Well done. Oh, okay. So Francis Howard has. Okay, we've got a couple questions here. Francis Howard, go ahead.
Okay, thank you, Doc. I wanted to get a little bit clarification because you spoke about line bundles and that's bundles from the Planck's constant. And with Poisson and symplectic, I'm actually aware of various forms that they could be in. That is when it is 2 in a dimension of 2n or 2n plus 1. But in your case, you gave a general view and you spoke about their line bundle. When I'm looking at line bundles or fiber bundles, I actually think of the base or the connectedness that are involved in the bundle. In your case, are you considering the symplectic form or the Poisson that you are using in your quantization to be a 2n manifold or a 2n plus 1 manifold?
2n or 2n plus 1.
Manifold.
Yeah, I'm not.
In the symplectic case, it's always even dimensional if it's finite dimensional.
Yeah,
so I'm not sure what 2n plus 1. Are you thinking of contact manifolds?
Yes, it's a bit of, it lifts a bit. Sometimes when you have the symplectic and there is a 2n, then you can have a 2n plus 1 that goes to the co-symplectic stages.
Oh, right. I don't.
Because I'm actually finding it a bit difficult to understand. Your quantization, yes, is clear, but you place a star algebra.
Sorry, I didn't understand your last sentence. What was the last statement? What is a star algebra?
Oh, I think he
still with us.
Okay.
Yeah. Eli, did you understand the last statement?
Well, he stopped halfway through a sentence, so I didn't understand that sentence. But but I'm not sure what he means by co-symplectic. I've never heard of such a thing.
Okay, we can.
Symplectic is always even dimensional.
Okay,
yeah,
so we've got another question here. So go. So Mogab?
But we can come back to it maybe later. Yeah.
Fair enough. Okay. So Mogab?
Hi. Yeah. Thanks.
Hello.
Thank you again for the talk. In looking at the abstract for the paper, you end with that this construction suggests a natural generalization to less linear examples. So I was hoping you could highlight what was missing compared to, I think you were comparing it to the Sorkin-Johnson state. What was missing in that made it less friendly to nonlinear examples, and how you can work around that?
Sure. I mean, it is essentially a construction for a distinguished state for quadratic theory. So let's say a free scalar field in this case. Why? Well, I mean, it's essentially based on the idea that you have your Poisson bivector, and then this function W is kind of constructed from that. But your Poisson bivector you start with is constant. Okay, so that then your star product is given in terms of like this exponential of a bidifferential operator with the kernel given by W. But so this is this Moyal-Weil definition of a star product. But that makes sense, of course, only for well, at most quadratic action, so that the Poisson bivector is constant. Otherwise, you would have problems with associativity. Like so that, I mean, there are ways around it. You could do some sort of perturbation theory. That's what we usually do in perturbative AQFT. But our aim is kind of to have something non-perturbative, and therefore, like, you know, the feeling is that geometric quantization, I mean, using the ideas we have presented, this is less, well, it's not reliable on this particular, you know, constancy of the Poisson bivector. So that's why we hope that this would, you know, provide the non-perturbative construction of distinguished states also beyond the free theory. But yeah, you asked me to, point to the particular thing that goes wrong. Well, the particular thing that goes wrong is that the Poisson vector is no longer constant. So this W is also no longer constant. Hence, the exponential formula for the product doesn't work. And this construction of algebra has to be modified. And hence the state.
Yeah, so the simple construction of the star product doesn't work. Plus, Sorkin-Johnson construction basically is just for a vector space. Now, we showed that with this geometric quantization construction, you apply that to the case of a vector space with a constant symplectic structure and an inner product, and it gives back the Sorkin-Johnson state. However, the geometric quantization construction is more general. You could start with, instead of a symplectic vector space with a constant inner product, just a symplectic manifold with some Riemannian metric on it. And you would get a star product out of the geometric quantization construction from that. And if you have a distinguished point on your symplectic manifold, you would get a distinguished state from that. And this would have what we did here as a special case of that, but it's more general.
Okay, thank you.
Yeah, thanks for the question.
Do we have any more questions? Well, now may be a good time to close things off. So thank you so much, Kasia, for
thank you. Thanks for your patience and understanding.
Not at all. I think you really dealt with everything very gracefully. It was impressive. Thank you for giving such a wonderful talk, and thank you to everybody for showing up and for all of your questions. Our next talk is scheduled in 2 weeks on the 15th of May, 7 p.m. Berlin time. So that's 1 hour later than usual. We've got John Bias, who is back by popular demand. John will be, yeah. He's going to be speaking for us on part 2 of what he and others call the tenfold way. So thank you again.
Incredible.
Yeah.
Thank you.
Thank you for, yes, go ahead.
If I can do some advertising, I will be in Berlin next week, actually. So
very good. Okay.
if there are more questions and people want to discuss, I'm happy to, meet up, and yeah, maybe we can talk about it later.
Absolutely. This is actually quite an international crowd. So the people that have shown up, I think, are really scattered all over the world. But I'll be in Berlin.
I will also be in Perimeter in August.
Oh my goodness. I think there probably are some people in the crowd from Perimeter as well too. So. All good.
All righty. Thank you. Thank you again.
Yeah, my pleasure. Thanks again for giving such a great talk, and also to your collaborators for chipping in.
Thank you, guys. Bye.